Okay. All right, and we are good. All right, thank you everyone for coming. I especially want to thank members of my committee, Dr. Sheehan, my advisor, for being here. Dr. Hoover, coming from biology. Really glad that you were able to make it for this, present a little bit of a different perspective than we're used to. And Dr. Schwartz, also on my committee. So today I'm here to talk to you about future of artificial intelligence and building a mind. But I'd like to start out with a quote. Supposing, for instance, that the fundamental relations of pitch sounds in the science of harmony and a musical composition were susceptible of such expression and adaptations, the analytical engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. That's a bit of a mouthful. This was originally said in English, but I wonder, can anyone guess when this was said? It's trying to say there is a machine that could compose music just as any human might be able to do. Something that we often see as a height of human creativity. When do you think this was said? Go ahead, any guesses?
In the 40s.
The 40s, that's a good guess.
18.
The answer, Evan's right. This was actually said in 1842.
Wow.
Yes.
Well, that was just a guess. That is a damn lucky guess.
Well, I think you knew it.
Oh, gotcha.
Bonus points. Does anybody know who said it?
Lovelace.
Ada Lovelace, the world's first computer programmer, said this in 1842. And she's one of my heroes, a very good representation of women in STEM. So I really love pulling this up. That
I didn't even know computers were a thing in the 1800s.
they weren't, and it wasn't until about 100 years later that ENIAC was the first digital computer that was created. But this analytical engine that was conceived at the time by Charles Babbage, and Ada Lovelace worked on it as well, was a mechanical version of a programmable computer.
Interesting.
So the point is, we've been thinking about machines that can act like humans for a long time. Bringing it about 100 years later, we see Alan Turing in 1950 wrote a paper. In it, he discussed something he called the imitation game. The rules of his game are that we take two participants, a man and a woman. We hide them behind some curtains so they can't communicate with each other. In fact, the only way they can communicate is through like a text prompt. And we have a third person involved, a judge. The goal of the man is to convince the judge that he's the woman. The goal of the woman is to convince the judge that she's the woman, he's the man. So we have one telling the truth, one trying to lie. So is the judge going to be able to tell just through text correspondence and asking questions, who is the man and who is the woman? And, I think most people would agree that it's a playable game. The judge may not always get it right, but it's something that can happen. So then he asked, what if we take the man and replace it with a computer? Could it be possible that we could still play the game? Could it be possible that the computer could fool the judge into thinking it's a man? These were really deep questions for the 1950s. In fact, Alan Turing thought that by the end of the 1900s, that you could say a computer was thinking without being questioned. So he really thought there was a real possibility that the computer could win this little game. And that's where the idea of the Turing test comes from. So where are we now? We're a little bit past the end of the 19th century, 1900s. We're not quite there where a computer has beaten the Turing test. But computers and AI programs have beaten the world's best players in a lot of different games. In chess and Go, Jeopardy, Texas Hold'em.
Oh yeah, I heard also like a very recent thing is AI art.
AI art has been very recent, and there's a lot of controversy over that. But it's an example of a computer doing what a human being can do, is only thought to do.
I actually use AI art for a project here at this very school.
Yeah,
Sweet.
so it's very prevalent, and it asks a lot of questions about what the potential of computers is. But most of these programs that we're using, most of these intelligences aren't a general intelligence. They may be extremely good at one particular thing, but that's all they can do. They don't have the general intelligence of a 7-year-old. You know, you can take the world's best chess program, can beat any human, ask it to open a door, it won't know what you're asking. It only knows how to play chess. So can we do this? Can we make a program that's more like a human? Maybe we've been using the wrong approach at this. Maybe we're looking at the problem wrong. Instead of trying to create solutions to particular problems, maybe we should start from the ground up and try to build an intelligent system. And we know that intelligence exists. We already have it in our own brains, or at least we like to think we're intelligent. So can we do that? Can we model an intelligent system on our own brains? Well, to answer that question, I looked at this paper that was published in 2021, a little more than a year ago, excuse me. Single cortical neurons as deep artificial neural networks by David Benioff and others. So what he did is he took a model of a brain cell and made a neural network, a computer program that would act just like that cell. So I wanted to see, first of all, if I could replicate that work. But a lot goes into this. Emulating brains is a very difficult subject. We have barely scratched the surface of this. It draws on a lot of different disciplines, including chemistry, physics, philosophy, most importantly, neuroscience and computer science. And that's what I'm going to be focusing on here today. So to start out, we want to look at what exactly a brain cell is. And I have a model of one here. So this is what a general neuron in brain looks like. It has a number of parts to it. It is a cell, just like any other cell in the body. So there are some similarities there. It has a cell body, which is called the soma. The nucleus of the cell is in there. It's got all these little tendrils called dendrites. And all along each of those dendrites are synapses. Each of those synapses is where it connects to another cell. And that's how neurons communicate, by passing signals through synapses onto the next. Now, the particular cell that they used is one called a layer 5 pyramidal cortical neuron. And it's only one of many different types of cells, but these are easier to study because they tend to be large cells and there are a lot of them in the brain. So these are found in the neocortex, which is the outer surface of the brain, and it's responsible for most signal propagation in the brain. So they are very long. And layer 5 means that they start here in this layer. You can see in the diagram, they're the biggest cells, but then they also have their dendrites stretching up through all the layers to the top surface of the brain. And this is what allows it to communicate across long distances in the brain. All right. Now, the actual communication itself is complicated, and I'm not going to get into the specifics of it here. But what happens is when a cell fires, it releases a number of neurotransmitters. And what these neurotransmitters do is they'll travel to the next cell it's connected to in that synapse. And it will bind onto one of these receptors. And when it's bound, that allows the receptor to open up. And opening up gives it an influx of these positively charged ions. So this whole process, basically what it does is change the electrical potential of the cell. And that's the main function of how it works. If you track that potential of a cell over time, you'll see that it varies. But when it hits a certain threshold, it will suddenly spike way up. And that's what we call an action potential. After the spike, it will return back to normal and continue on. But this spike here is what causes the signal to propagate and release neurotransmitters to the next cell down the line. So that's the basics of how the neuron works. Very, very simplified. The other side of things is the computer science side. So we're looking at neural networks here. Neural network is at its most basic way of machine learning used to train circuits. And it allows many, many variables to interact in complex ways. This diagram here is a very simplified neural network. It's got three main components. The inputs to it, these hidden layers, one or more, and the outputs. So what happens when you run the model is it takes the inputs, whatever you give it, passes it through all these hidden layers, and it ends up coming to an output. And whatever that output is its prediction. If you have at least three hidden layers, that makes it a deep neural network or a DNN. And then when each node in a hidden layer is connected to all of the previous, then it's a fully connected deep neural network. This one is not fully connected. All right, and the other important part about neural networks is that they are supervised learning models, which means that they depend on being trained with labeled data that has been provided to it. The training process involves starting with random weights for each of the nodes, and it will take the inputs, send it through the network. Each input gets multiplied by the weight for the node. If it hits a certain threshold, called the activation through the activation function, it will pass the signal along to the next set of nodes it's connected to. So let's see, yep. The process of training then is a matter of comparing the output to the expected value that is in that labeled data set. We want to see how far away the prediction was. And our goal in training is to minimize that difference. The less difference there is, the more accurate its prediction. It's predicting what it actually should have. So minimizing a number is a calculus problem. And hopefully everyone here has done calculus. So what it does, after it makes the prediction, we see the difference. It will adjust the weights of the previous layer to minimize those differences. And then it will go and minimize the layer between before that. And it will keep going to the inputs. And that's the process of backpropagation. And it will keep repeating this process on data sets until the weights stay relatively constant. At that point, you could say it's been trained on the data set. So this wasn't good enough for the authors of the paper. They had to complicate their neural network even more. So they added this concept called convolution. And what this does is it's largely used in image processing. And that's because there's two problems when you're trying to take a picture as an input. Number one is that pixels don't exist in isolation. That if you take a single pixel, it's related to the other ones that are near it. And if you get information from one, you've basically gotten the information from the other ones around it. And then the other problem is that there's a huge number of pixels that are involved in images. A single 1080 resolution image has over 2 million pixels. That's a lot of inputs. So it uses this process of convolution, which is instead of using a single weight for each input, it uses a pattern of weights it can apply to a grid of inputs. And that's what this image here is showing. It takes this 3x3 grid, applies the pattern of weights to it, and it gets one value as a result. So with that, we're solving both problems. We're taking neighbors into account, so that's going to be adjusted for. And we're also reducing the number of inputs that we're dealing with. That wasn't enough for Benioff. They also added this temporal aspect to it to make it a temporal convolutional neural network, or a TCN. And they added this because the current state of the electrical potential of the cell depends on all the previous states. They don't exist separately. So it's a process over time. And because of that, it doesn't take just one time slice as input. It takes in a bunch of them all at once. For example, if we say that the previous 99 seconds determines the 100th second, then the input would be those previous 99 seconds. We get the prediction for the 100th, so then the next input would be the second through 100th to predict the 101st. So it considerably increases the amount of data you're working with, which is why the convolution is so important. All right, so with this understanding, we can start to look at what the paper actually did. They took various different models, from a very simple ball and stick model to a complicated TCN, trained them on large sets of data, and then evaluated their performance on new ones. The model predicted both the membrane potential of the cell in voltage, which is that spike train that you see, and also separately if a spike occurs during that millisecond or not. The most accurate model they reported was a TCN with 7 hidden layers and 128 nodes per layer. And this one processed 1,278 inputs. So that's 1278 signals from other cells once every millisecond. And it did it in 153 millisecond sections for a total of 6,000 milliseconds per simulation. So there's a lot of data going on here. And this is a diagram of the TCN itself that I use. There's a lot omitted there here, just for clarity. There's 5 hidden layers missing, and 1,000, 1,200, more than 1,200. There's a lot of nodes that are omitted just so it can all fit on here. But after processing through there, it comes to an output, voltage, and a spike. Another important thing to note in here is alongside the convolutional step in each hidden layer, it has this batch normalization. All that does is try to regulate the scale of the numbers to make sure they don't get out of control. Usually it tries to clamp it between 0 and 1. So if you've got everything scaled to between 0 and 1, things don't get out of hand. You know, if you start getting crazy numbers after that. So for the replication of their work itself, all of the models and the code to run them were provided by the author in various repositories. Kaggle had most of it. GitHub had some. The models they provided all use Keras, which is a Python library that implements Google's TensorFlow. So it's a very well-known AI deep learning software library, and people know how to use it, and it's very powerful. The data sets they use for the training and validation were also provided. So I was able to get all of this from their website, and I had to piece together their Python code to be able to run the model. I selected one data set that they had tested on, ran it through the model again to see what it would say. This is the output that was programmed for it to provide. And there's a lot going on here we don't have to worry about. The important things are the spike train and the ROC, which I'm going to go into that. So this here is the voltage over time that it came up with. The cyan is what the neural network predicted. The magenta is the actual. And then where they overlap, it causes that blue color. So you can see from this that the model matched very well with what the inputs were. And this box here is just a blow up of this data here. So it is very close to what the predicted should be. The other measurement of whether it's spiked or not is measured using what's called a receiver operator characteristic curve, which is that thing there. And all of that is a plot of its false positives to its true positives. And it varies depending on what threshold you use for your outputs. If you use a very low threshold, you basically accept anything as a positive. So you're going to have a very high false positive rate. If you choose a high threshold, you're going to be more sure that you're only getting true positives, but you're going to miss some true positives as well. So the main measurement of this ROC curve is the area under it. The closer that area is to 1, the more accurate the model. They reported an AUC of, no, actually, this was what I got, 0.9926. Some other metrics they reported was the explained variance, which is the percent of the variation in the data that can be explained by the model. The root mean squared error here, and the mean average error. Mean average error is easier to understand. It's basically just an average of how far off each of the predictions are. So the smaller that number, the closer it is to the actual values. So comparing that to what was actually published, they reported an AUC of 0.9911. When I ran it, I got 0.9926. And variance, I was, what, 0.6. 0.5 greater and had a lower RMSE. So overall, when I ran it, it actually performed better than what they reported. So given all this, it looks like a match. I could say that the model they provided did exactly what they claimed it would. But how about trying new data? I thought this might have been a little too easy, so I decided to torture myself. To do that, I had to find out how they made their data in the first place. So you could collect data from actual neurons. There are devices called voltage clamps that you can connect to neurons to actually record the voltage in a petri dish. That would be excruciating and actually impossible for the amount of data needed to train a neural network. So what they did instead Because the cell behavior depends on some very clearly defined physical properties. You know, very clear chemical and electrical laws. We can calculate what the output of a cell should be, or the state of a cell should be, based on what's going on with it. And they did that with this Neuron program, which comes from Yale, actually. It uses Python, Hoke, and NModel to create these models, do the calculations for the voltages and spikes, and then output them. You can build cells using the various parts that actually have biophysical counterparts, like the dendrite sections, individual synapses, and even individual receptors in the synapses. And this here is a short example of some of the code that I use to build these synapses. It goes through the number of dendrites that I have in the model. And then for each section in the dendrite, it creates an excitatory synapse with these different properties that were all listed in the paper. And it creates a object that actually will stimulate that particular synapse over time. And then a listener to check for what the responses of that are. So going into that, we have to look at how the inputs, the stimulations, are created. And the model uses different distributions to come up with the times that each receptor receives a signal. And in the paper, they used a Poisson distribution, which is a rate over time type of distribution. I had a lot of trouble trying to get that to work. It continually crashed on me anytime I tried to use it. So I ended up using a normal distribution instead, which is a distribution centered around a mean and has an even dispersion. So when I did that, I was able to build this model and get it to generate an output. Okay. Yes, look like. And this is the output that it produced. So this is the Neuron program actually calculating the voltage of the cell at every point in time based on the inputs to all of those receptors. And this is what I got. And I said, that looks like a cell signal to me, so I'll go with it. Next problem I ran into was pickles, because the data was read into the model using these pickle files. And pickle is a serialized data format like a JSON, except for it's in binary, so you can't read it directly. Fortunately, the Neuron output is plain text, so I could read that. But I needed to find out what the table structure was for the pickles to be able to convert the output from the plain text Neuron output to the pickles that could be read by the model. And this was not fun, I'll tell you that. Each file was 1.2 gigabytes of data as text. And I had to look through that to find what the keys were so I can assign things correctly. I ended up in the program itself that ran the model. When it loaded the pickle, it pulled out the keys, and I was able to get the keys from that. And I was able to rebuild the table structure. So finally, with a data file, I could test the new data. So results. That's what Benigweb came up with. This was mine. The cyan, again, is the predicted, or the actual. Magenta is the predicted. So you can see here, this was way off. And not even close. And looking at the comparison of the ROC curves. If this is a straight vertical line, it basically means that there's no relation between false and true positives, that it's just random. So the model did exceptionally poorly at this. Another clue I had to that was this negative variance I had. Because the variance is usually a squared amount. It's the R value squared. So you don't usually get a negative number from that. There are other calculations that I found that do end up subtracting from 1. That's how it ended up being a negative. But this shows it was exceptionally poor at predicting the data. I mean, you can see from the other values here, like the root mean squared error was 5, 6, 7 sometimes more. So yeah, it was not a good model at all. What happened? Well, I know exactly what happened. The model performed exactly how I expected it would with their data. It did what they said it would. But yeah, it did not match mine at all. Most likely it's because of the normal distribution. That the type of inputs that it had as that distribution over time really made a difference. So I'm thinking if I would have gone through and spent the time to troubleshoot that and figure out why the Poisson wasn't working, it would have been much more accurate. But it did give me some potential insights into the paper. So one potential flaw with the model is asking exactly what kind of neuron behavior it was modeling. Because as a biophysical model, the neuron that produced the data was able to handle my inputs, and it did produce an output. I don't know how realistic that output is, but it is an output. It is something that a cell could do. What about their Poisson? Is that what a neuron normally does? That is something I could research further, find out how close their model was to actually imitating the behavior of a real neuron. So yeah, so what's still able to produce outputs? Is the Poisson representative? That's my question there. One important finding from this was the amount of speed up that they got from running the PCN versus the neuron calculations. All of those differential equations are very slow and very difficult to do. The 128 simulations to generate the data took my PC about 6 hours to run. When I took the same data and put it through the neuron model, the Keras neural network, less than 7 minutes. So that's about 5,300 times faster. So this opens up a lot of possibilities for neuron modeling, especially the idea of modeling neurons in real time in networks to see how they behave with each other. Another question I examined while looking at these neurons was the phenomenon of long-term potentiation. What that is when a neuron receives a very strong input, it will tend to create more receptors at that synapse. And what that does is cause it to be more sensitive to further inputs from that cell. The more sensitive it is, the more likely it is to fire. And this is what we call neuroplasticity. And this is what we think a lot of learning and memory is based on. So I wanted to see if the model would be able to do that. But it didn't take me long to realize that it couldn't possibly do it because the LTP process requires the cell itself to change in response to the inputs. And a neural network, once trained, or this particular model, cannot change. those weights are fixed. And they won't be changed no matter what input it gets. So a different type of model would be needed to accurately model this kind of behavior from a neuron. So next steps. We want to look at what real neuron inputs look like. How close was this to actually modeling it? Generate a better data set that actually matches the results they had. And especially using reinforcement learning rather than supervised learning to model that long-term potentiation, to see if we could get realistic behavior that way. So I like to think this little work here, it's not much. It's just one step along the way to building a mind. Thank you. Are there any questions? Okay. Yes.
So did you try contacting the authors about the song?
I had not contacted him about that. I contacted him early on about, I'm going to try replicating your work. And he said, okay, that's cool. Let me know. Kind of brushed me off. So I haven't heard back from him since. I was going to email him and say, I'm sorry what I did to your work, but here.
Well, I think it would be worth asking him.
Yes.
Like for his piece of the code that was doing with the song. And also why he chose that. Because, I assume it doesn't really defend that in his original work.
Yeah, in the footnotes of the paper where it describes his methods for each of the models, he lists that it used the Poisson with certain characteristics, and then he also used a Gaussian smoothing for it and some other process he did to it, and he claimed that it made the data more varied to more accurately model neurons, but didn't really back that up. Or at least I didn't dig enough into the literature to find out where he got that claim from. Yes, Sam.
Is there any way for you to compare the data that was generated to actual data from neurons and just see if it's the song, if it's actually realistic?
And that's where my experience in neuroscience isn't enough to really tell, because when I had that normal distribution, it's probably way back. I said, you know what, this kind of looks like a neuron. I think I went too far. And I said, you know what, this looks close enough, but if I had actually known more about what it should look like, I probably would have seen that, yeah, this is all wrong. I think that looking at this is probably a good one. Yeah. It's not playing. There it is. Yeah, so this is the voltage that it produced. And I was mostly looking at the behavior down here at its resting state, and not as much as at the spikes. And I did see things like this, which concerned me a little bit, because this should not be possible. It should only be a single spike. But I wasn't quite sure what to do with that, so I let it go. Yes, Doctor.
So with regard to the Poisson distribution, when neurotransmitters bind to a receptor, they open the ion channel,
Mhm.
and then the channel conducts a given amount of current that can be measured. Might be say 2 picoohms. If there's additional neurotransmitter to open other channels, then the amount of input current is multiples of that 2 picoohms.
Mhm.
So that's why I'm guessing that he used a Poisson distribution.
That
Because
makes sense.
Because in real life, that would be the input by to learn.
Mhm. I still think that, the Poisson distribution isn't going to model the neuron under all circumstances. It's just going to model the general normal operation type thing. You know, I looked into epilepsy a little bit. And during a seizure, all the neurons fire together. And it causes a signal worse than this. So, you know, there's different things that the physical system can do that haven't been captured by any of the data that has been trained or used to train the models.
So this is like a mini seizure then?
Probably. Probably. You would not want your brain doing this. Any other questions? No? All right. Well, thank you guys so very much. I really appreciate you coming. See my work. All right. And now you're going to kick us out. There it goes.